Angular acceleration is the rate of change of angular velocity over time. Angular velocity is the rate of change of the angle that a wind turbine is turning over time. And then that all relates to the angle in general that wind turbine is turning, and the angle looks like this. And that position changes over time. So we have that position changing over time called velocity. We have that changing over time, which is called acceleration. And we hope for our physics calculations that angular acceleration is constant. And we like a constant angular acceleration. That doesn't mean it's not spinning. It can be spinning really, really fast at a constant acceleration, or it can be spinning really, really slow at a constant acceleration. But it means that it's not changing its speed. It's not accelerating or it's not decelerating. But getting a constant acceleration is very difficult in the context of a wind turbine, because wind turbines are governed by the tangential velocity V. The tangential velocity V comes from wind in a wind turbine. And since that tangential velocity comes from wind, it is governed by the unknown and you can't change it, and it is inherently variable. So if I have a variable, a variable input of tangential velocity V, then that means I have a variable rate of change of the angle, which means that this is variable. It's a variable speed. And if the speed is varying, then that means by definition, it is accelerating and it's decelerating. So it's not, so acceleration is not, it's not zero. It's not, it's not going all one speed. Now think about acceleration being zero. Can you be moving if acceleration is zero? Absolutely. So think about yourself on Highway 401, then you're traveling at 100 kilometers per hour because that's the speed limit. So you're traveling at a constant velocity of 100 kilometers per hour. Then that means that your acceleration is zero. Acceleration being zero doesn't mean you've stopped. Velocity being zero means you've covered no distance over time. But if you're traveling at a constant velocity, then your acceleration is zero. And it really helps our calculations when acceleration is zero. But in the case of these rotational problems of a wind turbine, the acceleration is not typically zero. All right, so it's important to know the differences there between acceleration. So acceleration has this symbol, which is a small alpha, and the relationships that relate acceleration to angular velocity are shown here, and they're very much the same as the relationships that related these in a tangential manner. Now, torque is a very important concept. Torque means how it's a measure of the force as it's applied over an angular displacement. So torque is governs how much work can be done on an object. So how much force is applied over an angular displacement. So let's think about the wrench example, because that's a classic example of torque. So here's a wrench and it's going to be around a bolt. Here's a wrench, it's sitting around a bolt and it has a handle. Now, this is the point of rotation of this bolt. And in here, I can show that this bolt is going to displace an angle. It's going to probably displace that angle over time, which is called angular velocity, displacement over time. And then even, probably since you're starting at zero and you're going to be moving, that means there will be also an angular acceleration, which is going to be that angular velocity over time. All right, all of these things are going to happen, but the torque equation or the torque concept or the torque explanation of math explaining a real world thing takes into account the force and where it is applied, depending on the object. So let's just get the concept of torque through our heads first. Now, if I ask a child to turn this wrench, then the child does not have a lot of life experience, and the child is probably going to turn it maybe in the right direction, and they're going to turn this wrench by putting their hands here, and they're going to be pressing down like this with a force. And that's going to make this turn, and all is good, and you're going to have something happening, right? However, if I ask an adult who has some life experience to turn this, then they're going to put this force here at the end, because they can tell from life experience that the distance d1 versus d2, they have learned that matters. They have somewhere along their life learned that this distance delta d actually makes the job easier. So if you were to apply it as the child did, then you're going to have to apply a much larger force. If you apply it at the end, then your force can be much smaller to do the same amount of work, and the work is moving this angle over time. So this is a concept of torque. You've all done it. You've all tried to move a rotating object with a force. And that's what torque is. But now I need to turn that into an application of a wind turbine. So let's look at torque from the perspective of a wind turbine. Well, that's a completely different thing. So now from the perspective of a wind turbine, this doesn't look the same. You can't govern that force that's being put on it. So, and that force is going to be variable. So now that force that is turning these blades, there's 3 of them. That force that is turning them is going to be the tangential force that is applied, that goes in the same distance as the tangential velocity. This is tangent. This is tangent. So 90 degrees to the circle. And this is a force. Now, it's important to remember where that force comes from. That force comes from the wind, which is completely out of your control. So there's a force, and it's sometimes strong and it's sometimes weak. Not only does it have a different velocity, but it has a different force being applied. Now, I'm going to simplify my wind turbine, and I'm going to assume my wind turbine is a disc. And that's a pretty bad disc. So now I'm going to do it again. I'm going to simplify my wind turbine, and I'm going to assume it's a disc. All right, now my force coming in from the wind, which is variable, my force now has to turn this rotating disc, and it's going to rotate just like my wrench did. It's going to turn an angle. It's going to turn that angle at a rate over time called omega. And it's going to turn that rate of change of displacement is going to be changing over time, which is called angular acceleration, alpha. All of these things are going to happen. And they're all going to be happy for us because they're all going to help us make wind. Specifically, it's the omega we want to make wind. We would rather the acceleration be 0. We would rather a constant omega, but we don't get that from the wind. So let's not talk about the velocity of the wind anymore. Let's talk about the force of the wind. Now the force has to move these three blades, which I am stylizing as a disc right now. And the amount of torque you're going to get from that, the amount of torque you're going to end up getting, right? Torque is force times displacement, like I showed you with the wrench. As displacement is higher, for whatever force, you're getting more torque. Torque is the work done by a force over a distance. So I'm going to write that down here. Torque is the work done by a force over a distance. And when you were young, you learned that you can do more work with your force if you put it over a bigger distance. Work done by a force at a distance. So immediately I know something really simple about this. Immediately I know that I can get more torque. I can get more torque if my blades are bigger and my radius is bigger. But in a wind turbine, we have to think about it backwards. So now I see these blades. If they're bigger, I'm not saying I get more torque. I'm going to say I need more torque. So in a wind program or a wind project or math, we have to say how much force do we need to overcome? How much force do we need? So, how much torque are we going to need? So how much torque do we need to generate is our question. How much torque do we need to generate? How much torque do we need to generate in order to get this thing spinning? And the key answer to that, how much torque do we need to generate to keep that thing spinning? Well, it depends on how much it's accelerating or decelerating. And it depends on I, which is moment of inertia. This is highly dependent on moment of inertia. So I is the answer. And what is I? It's moment of inertia. Inertia means how much does it take to get something going? How much does it take to make it stop? A flywheel is a classic example. A flywheel on an old internal combustion engine was a big disc of steel. That big disc of steel had a lot of mass on the outside of it. That big disc of steel took a lot of torque to get it spinning. But the reason it was there is because once that engine has spun it, it'll keep it spinning. So now I have this giant disc and I'm going to say, whoa, how much torque is it going to take to get this thing spinning? Well, that's one of the reasons why it's actually 3 light blades. If this is actually 3 light blades, then think about it from common sense. It's going to take less torque, less force. I could have a smaller radius and a smaller force because it's going to require me to put in less force over distance to get the work done of creating that angular velocity. It means that there was less inertia in order to move. Now think about this as a giant transport truck on each blade that you're going to have to spin. A giant transport truck that's not very aerodynamic and it's really, really, really heavy and it's really, really, really big. That's really hard to get going. Therefore, it requires more force displaced over a larger distance. And that means more torque. So it depends on the nature of the item that you're spinning, it depends on the moment of inertia. In order to get a velocity from a force times a distance, it depends on what you're spinning. So I'm going to type in here, how heavy is it? How light? How is the mass distributed? If I think I spelled that wrong. If I have a whole bunch of mass, if these blades have all of their mass at the edge, oops, if these blades have all of their mass at the corners, and they're really skinny in between, then that's going to be harder to start spinning than if the mass were sitting over here. Because think about it, in real life, is it harder to spin something that has mass out here? Or is it harder to spin something with the mass at the center? Of course, it's easier to spin something with its mass at the center. Now, if these blades were really, really thick, if this were a disc and it's really, really thick, is it going to be harder to spin or easier to spin? It's going to be harder to spin if it's a thick disc. If it's a thin disc, it's going to be easier to spin. So the amount of torque that you have to apply would be less. The amount of force from the wind gets to be less in order to have that angular acceleration work. That's all governed by the geometry of that object. The geometry of the object is described by moment of inertia. The geometry of the object is described by moment of inertia, and moment of inertia simply says how much mass, is it a heavy disk or a light disk, and where is it placed? How much mass and where is it placed? Take a look at that formula. It says how much mass in kilograms and where is it placed in meters squared from the axis. It matters. So mass matters and distance from a spinning axis matter, and that's the definition of moment of inertia. So here's the formula for moment of inertia. The formula for moment of inertia, I've just rearranged the torque formula. I rearranged the torque formula to solve for I, and what I get once I torque is in Newton meters, angular acceleration is in meter per second, and then over meter per second again. No, times meter. Oh, it's meter per second squared per meter, and then once these cross out because a Newton is a kilogram meter per second squared, we know. So then the meter per second squared cross out, and then I have a 1 over meter in the denominator here, which goes up, and it gets this m squared. So it works out that moment of inertia is mass times how far away that mass is in displacement. Now, what the number is for the moment of inertia is different for everything. What the number is for moment of inertia depends on the shape of the object. So here we go. If it's a point mass rotating, should be pretty easy to get this rotating, right? Should be pretty easy to get this rotating. If that mass were distributed over a disk, it's a little bit, well, actually, it's kind of, if I were to compare the two, this is actually a little bit harder to get moving than this one. because the mass is distributed further from the axis. If you turn that same mass into a disk, it's closer to the axis, so it's a little bit easier to rotate. If you take this disk and you stick a hole in it, and then you stick all of that mass again way out at the edges, this is going to be really hard to rotate. Right? Now, think about things that you would do to this. If you now make it heavier, if it's made out of lead, it'll be harder to rotate it. If it's made out of something very light, if it's aluminum, then it'll be easier to rotate. So I, for lead, would be big, right? It would be much bigger than I for aluminum, right? So now let's think about our wind turbine. What does our wind turbine actually look like? I like my nice green wind turbine blades. It actually looks like this. So it's something sort of in between. But what we do in wind turbine math is we take a shortcut, we kind of cheat. It's called an engineering estimate. We don't call things cheating, we call them engineering estimate. And we actually assume that a wind turbine acts like a solid disk at the radius equals the blade length. So the inertia, or the moment of inertia calculation for a wind turbine, we actually use this. Which might make you cringe because it's an engineering estimate. So we are going to use this equation in our formulas for estimating the moment of inertia for a wind turbine. Moment of inertia are really easy to calculate. There is no way to make it difficult. Moment of inertia is you simply have the mass and you have the geometry and you just need to calculate that. There's nothing hard about it.